I don't have the clickers today. I'm not sure if I will continue with the clickers. I'm kind of on the fence on those. Remember I said trying it out. I don't know how it's going to work out. And not because of this class, but in my one of my other classes, they didn't do well on the first test. It was a college algebra class. So I said, I'm not sure it's worth me bringing those, lugging them around, passing them out every day and all that if it's not going to show any like true result. Because remember I said I don't move on unless 80% of the students are okay. Well, if 80% of you are okay, but the test comes and you still don't do well, then I don't know if that's helping. So, all right, so we are going, there is no chapter in the book or no section in the book that is dedicated solely to Riemann sums. I like to spend some significant time on Riemann sums. So I'm calling this chapter R for Riemann, Riemann sums, and R1, it's going to be R1 through R, I think, 15 or something like that. So we are now, what we're doing now is this. We've spent the first few weeks trying to figure out how we can find antiderivatives. Tyler, put your phone away. Come on, man. So we've spent 6 weeks doing integration techniques, and now what we're going to do is take a step kind of back and try and figure out where this whole integration thing comes from, what we're going to use it for, you know, what is its value, right? Just finding antiderivatives, but who cares, right? Especially if I go to Wolfram Alpha and just type it in, like, you know, what's the point? So our motivation, this all starts with the area problem. So what is the formula for the area of a circle? Pi r squared, right? We're all comfortable with that. We've heard that for a long time. So where did that come from? Where does that formula pi r squared come from? You got me, right? I don't know. Someone? Is the burning bush and the tablets, the 10 Commandments on the backside was all the math formulas, right? No. So every formula had to be created by human ingenuity, right? We had to come up with it. So we're actually going to show where that formula comes from, hopefully next class. All right, maybe today. I might be able to knock it out today, just as an end to our lecture. So how, if we were sitting there trying to estimate this area, how could we do it? Now, for a long time, humans had no problem with the idea of finding the area of a rectangle. You know, you just have a rectangle, area is length times width, and that was fine. And when we were, you know, trying to, depending on your perspective on history of man, I think at some point in time, we realized that we needed to put boundaries on our shit, right? Like, this is mine, this is yours, and like, don't cross that line, and right? I mean, that was pretty natural to set up boundaries. And you know, so you'd want to know how much area you have, right? How much land you have. So, you know, finding areas of rectangles is no problem. But when they were weird shapes, it became a little harder. So a circle is one of the first hard shapes that we ran into finding the area of. So how could we find that area? That's the motivation. That's the problem that we would want to try and solve. So what we're going to do is we're going to approach it by a divide and conquer approach, or what's called the method of exhaustion. So imagine taking a circle, let me make this a little smaller. Imagine taking a circle, and right now, this number over here is going to represent the area that I'm approximating of this circle. Right now, I've done nothing. There's my circle. So I'm going to throw some things in there that I actually know I can measure the area of, like some triangles, right? Triangles are just parts of rectangles, aren't they? I mean, like, you could look at a triangle as like half a rectangle in some respects. So we should be able to figure out the area of those triangles. And the area of those triangles is 2. All right? Now, how could I get a better approximation? More triangles. So how about I do this? I make my triangles, there we go, like this. So they all start at the center and they go out like pieces of pizza almost, right? But with flat edges on them. And then what I can do is start adding those up. And so you can see now, look at my answer, 3, right? How could I get an even better approximation? Smaller triangles, right? Smaller and smaller triangles. And the more triangles I put, the smaller they get, the better approximation I would have, right? Make sense? By the way, this is the unit circle, so the radius is 1. So pi r squared, the true area, should be pi times 1 squared would be pi, 3.1415, right? So right now I'm getting close, right? 3.14. The drawback is I have to add up all those triangle areas, don't I? So I'd have to find a formula for each one of them. But I could get close, right? I could get close. And do you see why they call it the method of exhaustion? I mean, imagine physically having to go out and like measure out stuff like in someone's, circular plot of land or something. That'd be a pain, wouldn't it? But the idea is that we have n triangles and we add up the area of each one, and that would give us our approximation. Yes? Okay. Now I just threw this in here as a reminder. If you're given a triangle, everyone knows the area of a triangle is 1/2 base times height. But there's an alternative formula, and that's the formula right there. If you know two sides of a triangle and you know the angle between those two sides, then the area of the triangle is 1/2 AB sine theta. You probably saw that in pre-cal. Hopefully you saw that in pre-cal. Okay, so we have this idea of area of a circle. Let's just kind of put that on the side burner for now, and let's talk about something a little different, distances. Let's say a person walks at a constant speed of 2 miles per hour. So you're walking 2 miles per hour. How far have they gone after 3 hours? 6 miles, right? 6 miles. Right? That's nothing fancy there, 6 miles. Okay, so how is this solution geometrically related to the graph? So if I were to graph time on my x-axis and the speed of the person on the y-axis, then I have a constant speed of 2 miles per hour, right? Then how does the 6 come from this graph? Where is it in this graph? It's the area underneath that curve, isn't it? So if I take this, hold on, let me see if this is going to work. Yeah, no, that didn't like that. Okay, I always have to do this. Right, so if I take this and look at the area underneath, right? The width of this thing is 3, right? The height of this thing is 2. 3 times 2 is 6, which would represent the distance that we traveled, right? Is that a coincidence? No, that is actually what we would need to do, all right? So somehow finding the area underneath a function has some value, at least in this application, doesn't it? That's right, it's the antiderivative velocity. But again, we're not there yet. So now, what about this one? How far does this person go? Between hours 2 and 5. So let me put this in here. So this person has a different velocity. I'm not telling you what the velocity is or the speed of the person is at each moment in time. I give you a graph that represents it. But it's the same thing between 2 and 5, right? Then we'd need to find the area of this, wouldn't we? So how could we do that? Okay, so you can just create a rectangle here, and then you could create that triangle there, right? Can you tell me what the area of this is right here? So how wide is this? 4. How tall is it? 1. So that would be, the area of that would be 4. Y'all agree? And then what's the area of this one? Well, how wide is it? 4. Tall, 2. And then, is it 3? Oh, yeah, it's 3. Thank you. Hold on. I should write it down. This is 3, right? This is 1. This is what? 2. So the area of this one, I'll say the area of the triangle is 3 times 2, half of that, right? Half of base times height. So half of base times height, which would be 3. And the area of this rectangle is 3 times 1, which is 3. So the total area would be 6. So this person would have also traveled 6, miles, right? In that time between 2 and 5 hours. So there's nothing complicated here, I don't think. It's just, finding the area underneath rectangles and triangles, no problem. But how about this one? How far does this person go between hours 0 and 3? So now what we have is a curve, right? The function is x squared. So I'm telling you what this curve is, and we want to go between 0 and 3. A limit how? Okay, so y'all are getting the carriage in front of the horse. We don't know right now, unless you've seen this, we don't know that the relationship between this area and antiderivatives is this thing called definite integral. I'm not there yet, okay? It's like me walking in here and trying to teach a Cal 1 student what the derivative of x squared is, and everyone's like, 2x, because everyone's seen it, So I'm trying to get you to think about how you would approach this. You can't use something we don't know yet. So how could you approach it? You cannot draw the triangle and the rectangle like we did before because it's curved, isn't it? It's curved. So you're going to run into some issues if you try and get the exact area. So what we're going to do is use an approximation using rectangles. So let's take a look at this right here. We want to know the area under this blue curve. What I could do is I could cut this up into, let's say, 5 rectangles. I'm just going to pick an arbitrary number, 5. And then for each rectangle, I'm going to go to the right endpoint. I'm going to go up to the function. Whatever the value is there, I'm going to come over and draw that rectangle. So then I would take this right endpoint, I would go up to the function, come over, draw that one, and do that for 5 rectangles. If I add up the area of those rectangles, it should be easy, shouldn't it? Finding the area of each of those? Adding them all up, no problem. But the issue is that that answer is going to be too much, right? It's more than the true area. Agreed? Well, depends on what it is, right? So this is an over approximation. How could I get a better approximation? Make these rectangles not so wide, and that should reduce your error, shouldn't it? And that's what this idea of Riemann sums is. Riemann is the mathematician who kind of came up with the approach, if you want. So the more rectangles we have, the better the approximation. We will need a way of adding up many, many rectangles. So here I have a computer program that will do the same thing. Let me put that other one up there. So I'm going to put in those 5 rectangles. Can y'all read this? The estimated area using my 5 rectangles is 5.9979. The true area underneath that blue curve is 5.333 repeated, 5 1/3. So I'm off, right? Too much? We said if I put in more rectangles, it should get better. So let me put more rectangles in. There's 6 rectangles. Keep your eye on this number, 5.89, 5.82, 5.76, 72, 5.68, right? The more rectangles, the better my approximation. Just like with the circle, right? The more triangles I put in, the better the approximation. So this is starting to kind of lead to the idea of a limit, because if I could somehow let there be an infinite number of rectangles, wouldn't that somehow correspond to the true area? But what's wrong with that? I mean, how can you have an infinite number of rectangles in there? How wide would your rectangle be? It would be infinitesimally small, wouldn't it? Like practically 0. And if it's practically zero, then your width is zero, and you can't find an area of something that doesn't have width. So the question is it even possible to consider the idea of letting the number of rectangles become infinite, or the width of the rectangles becoming zero? And the answer is yes, because that's what the limit allowed us to do. It allowed us to actually see how things behave by allowing a value of x to approach something without actually ever getting there. And so we will have a way of addressing it. Now, there's something else that's subtle here. Let me go back to 5. This was an overestimate, right? And what I did was I created 5 rectangles. Let me go 4 rectangles so that our numbers land on good spots. See how it landed on 2, the next one's on 3, the next one's 4 and 5. Okay, so what I did is I went into 2, I plugged 2 into the function. That told me how high it was. In this case, it was 1, and then I created that rectangle. I plugged 3 into the rectangle, went up and over, and then 4, and then 5. What if instead of plugging in the right endpoint of the rectangle, I plug in the left endpoint? So I do this instead. So this first rectangle, the left endpoint is 1, right? How high is the function there? What's the height of the function here? 0, so I don't have any height to this rectangle. Then I go to this rectangle, I go to the left side, I go up and over and down. And then I do the same thing here, up, over to the right, down, up, over to the right, down. And now I do have 4 rectangles, 1, 2, 3, and this one's here, but it's nothing. If I add up those areas, I will get an approximation, correct? That approximation will be less than the true area. But again, if I start adding them up, here's my approximation, 4.14, no good. Trying to get to 5.3. More rectangles. See it coming up? But it's always going to stay underneath, right? 5.333. But as more rectangles go in, I get closer and closer. Yes? So I could have gone the right side or the left side. In fact, I could have, instead of going right side or left side, I could go what's called the midpoint. So here are my rectangles, right? Go to this rectangle. Instead of going up here on this side all the way to the top, or instead of going this side to the top, I go right to the middle of that little rectangle. I go straight up, and then from there I go out both sides. And I draw my rectangle. Does that make sense? I do that for each one of these. And then look at my area. It's hard to tell if this is going to be an overestimate or underestimate. So far it looks like it's a what? Over. If I start adding more rectangles, look at, man, I'm getting closer to that true answer fast, right? I mean, with 20-something rectangles, I'm already within 2 decimal, 3 decimal places, right? That's not bad. So you might be thinking, okay, well, the midpoint's the way to go because it's faster, right? It gets you there quicker. What's going to end up happening is that it's not going to matter, okay? You pick a right endpoint, you pick a left endpoint, you pick a midpoint, you pick any point. Does not matter which point you pick in that rectangle. Plug it into the function, draw your rectangle. As long as you let the number of rectangles become really large, they will all converge to the true answer. They're all going to get you there. All right, make sense? All right. So now, what we're going to do is we're going to estimate the area under the function f of x equals x squared on the interval 1, 5 using 4 different approaches. Now, this problem is to start to get you to look at how we would set up these Riemann sums, because our end goal here today is to have a formula to approximate the area, in fact, to find the true area underneath any curve. But to come up with that formula, we have to, start baby steps. So we're going to start with this. All right? And let me bring something else up. Take this picture here. Start a new page. Okay, so what I'm going to do is we're looking at the function f of x equals x squared we're looking at on the interval 1, 5, and we're going to do two rectangles, okay? Two rectangles. We're going to use the right endpoints. So help me come up with all the information I need for this. I've drawn it out for you, okay? Here's the function. Can you tell me how wide each of these are? 2. And they should be the same for everything, right? So what I want you to do is write this down. This right here, I'm going to call this my delta x. This is also my delta x. That's my change in x. That's how much the width of each rectangle is, how much x is going to change, right? Each time. What is delta x for each of those again, you said? 2. Now, the way we got delta x was by you looking, right, and seeing it. But we really did this. We took 5, we subtracted 1. 5 minus 1 gave us the total width of everything, right? 4? Yes? And then how many rectangles did we want? 2. So I divided that by 2, and that gave us 2. This 2 right here comes from this little formula. Noticing the connection here, the 5 is the endpoint to the right, 1 is the endpoint to the left, and 2 here was the number of rectangles. You following me? Again, we're trying to come up with a general formula down the road here, so we're going to have to be able to match it to something, and this is what we'll match it to. All right, so that's delta x. Tell me about the actual points right here. What are the x values at these points on the rectangles? So I'm saying, what are these points? 1, 3, and 5. Agreed? 1, 3, and 5? So I'm going to call these 3 points here x0, x1, and x2. We said x0 was 1, x1 was 3, and x2 was 5. Another thing I want you to recognize here is that x0 should always be what? If we do this, should always be the first number of the interval, right? And the last number, x, in this case, x sub 2, should always be what? The last number, right? And really, to get from here to here, and then from here to here, all we're doing is adding 2 each time. Would you agree? Adding 2 each time? And what's 2? Delta x, isn't it? So you could, if you wanted to, say that this is x0. This one is x0 plus what? Delta x. And this one is x0 plus 2 delta x's. Again, what I'm doing is I'm trying to, again, lead us to where we're headed later. We don't need anything that I've written down to find the area of these 2 rectangles. I understand that, right? Okay. At this point, let's find the heights of these rectangles. How tall are they? So how tall is this rectangle right here? We'll call that R1. The height of it right here is whatever we get when we plug 3 into our function, right? 3 squared is 9. So the height of that should be 9. What about this height? So that's 5 being plugged into our function. Our function is x squared. 5 squared is 25. So would you agree that this 9, right, this 9 is actually equal to f of 3, yes? Which is the same as f of x1, right? Because what's x1? x1 is 3, yeah? Which is the same as f of what? x naught plus delta x. What about the 25? What's that? That's f of 5, which I could also have written as f of x2, which I could also have written as f of x naught plus 2 delta x's. Any questions on this construction? All right, so let's talk about area. I think we have everything we need for area. The area of this, the area of my approximation, right? The area should be rectangle 1 plus rectangle 2. Agreed? What is the area? What is the area of rectangle 1? It's the width of the rectangle here, which is 2, times the height, which is 9. 2 times 9. But you know what? Let's do it this way. Let's do 9 times 2. We'll do height times width. Plus, what's the area of rectangle 2? 25 times the 2 again. And we could very easily compute what that is, right? 68? Okay, but hold on for a second. I want you to see something below this. Let's do this kind of written in terms of this. What was 9? 9 was the function. How far do we want to go? Let me do this. 9 is this, right? I'm going to actually write that. It's x naught plus delta x plus, now this one right here, oh, sorry, I'm missing something. What's behind that? That's 9. What's 2? Delta x, so times delta x. Then plus, what's 25? We said that was f of x naught plus 2 delta x. And then the 2 here was delta x times delta x. I'll point something out right now that's going to be nice in a second. Notice that we have 1 delta x here and 2 delta x's here, right? What do you think would happen had I cut this, instead of 2 rectangles, into 3 rectangles? How do you think this formula right here would change? We would have 1 more of them, wouldn't we? But what would also change, delta x wouldn't be the same. It wouldn't be 2 anymore, would it? But it would be something. Our x naught would still be x naught, wouldn't it? It would be the left endpoint of the where we started from. So what we're going to do is, if we have 10 of these, we're going to have f of x naught plus delta x times delta x plus f of x naught plus 2 delta x. Then we'll have the same thing, 3, then 4, then 5, then 6, then 7. Does that make sense? Okay, I hope so. All right, so we're done with this, right? We're done with this. We answered the question here was what? What's the approximate area? 68. That's what we got. But I'm trying to construct all this other stuff so we can go to our general formula. All right, the next part of the note says, do the same thing with 4 rectangles. Same thing with 4 rectangles. So let's try this one without me putting the graph up there for you. 4 rectangles. We're going to go from 1 to 5. Here goes up like this, right? That's what x squared looks like. I'm going to do 4 rectangles here. So how wide should each one be? So I'm going to start with my delta x. My delta x should be, remember my interval I'm put up here is 1, 5. My function is x squared. How wide should each one be? 1. So how are we getting that? We're taking the 5 minus 1 over 4 rectangles. That's 4 over 4 is 1. For this example and from here on out, these endpoints, I'm going to label them. I'm going to call them A and B. A and B. So that when you look at this formula for delta x, couldn't you look at this as being B minus A? Yes? All right. We'll do one more example after this, and you'll see how we'll start to the formula will start to pour out here. So there's delta x. What I need to figure out now is for these 4 rectangles, 1, 2, 3, for these 4 rectangles I'm going to do, what are these points that I'm going to have? So I'm trying to find these points right here. How many do I have? I have 5 of them, right? So what's x not equal to? 1. Which you could say is A, isn't it? Which is 1. What's x1 going to be? So now don't go try and say, okay, like if we cut it up, you know, like what would be halfway? Or just think about what we did last time. We started, and then to move to the next one, how much do we move by? Delta x, right? So the next one should be A plus delta x, good, which would be 2. And then the next one would be A plus 2 delta x, which would be 3. Then x3 would be A plus 3 delta x, which would be 4. And then finally, x sub 4 would be A plus 4 delta x's equals 5. God, I hope that makes sense. That makes sense? I mean, you could have said that x2 is x1 plus delta x, couldn't you? Or you could have said x3 is x2 plus delta x. But what we're doing is all of our formulas here, right, all of these have something in common. The only thing that changes is the coefficient of delta x, doesn't it? And that is going to be key to coming up with the general formula. Go ahead. Yes. Uh-huh. It's going to be n. That 4, you mean? That 4 is going to be the number of rectangles we have. You thought that what was going to be that? This right here is our x sub k. Yes. But you're ahead of me a little bit there. So this right here is the number of rectangles. Number rectangles. All right. Tell me about the rectangles here. We have 1, 2, 3, 4 of them, right? And so what we're going to do now is try and add them up. Add up the areas. Do you want to find the heights of each one first, or just go straight to the areas? Straight to areas? Okay, let's see if you can knock this out. Let me label my points here. X0's there, X1's here, X2's here, X3's here, X4's there. So I just labeled those points. All right, rectangle 1, give me the area. It's the width times the height, yes? So how tall, well, let's go height times width. How tall is it? 4? 2? Okay. Maybe we should go a little slower. I don't want to push too hard. I mean, we okay with 4? Let me write it as the formula first. It should be f of what? x1 times, that's the height, delta x. What is f of x1? That's f of a plus, I'm gonna do it at the end. A plus delta x, right? Times delta x. But that's f of, what was a plus delta x? 2. So f of 2 times what was delta x? 1. What's f of 2? 4 times 1, so 4. That makes sense? What's rectangle 2? F of x2 times delta x. That's f of a plus 2 delta x times delta x. What is f of a plus 2 delta x? 3, right? That's f of 3 times delta x, or delta x was 1. So what's f of 3? 9. 9 times 1 is 9. So we get 9. We got to do this, what, 2 more times? You get the pattern, though? And then we add them all up. So let's see if you can get the next one. What's the next one, R3 going to be? Don't write it all down. Just the final answer would be 16, then R4 would be 25. Add them all up. 16 plus 25. So this is 41, 54, 54 total. What was our answer when we had 2 rectangles? 68. Now we're down to 54. So we're getting closer to the true area, which was what? Like 53 point. It was 41? Okay. Oh yeah, I was doing a different function earlier. I'm sorry. Any questions? All right, I think from the look of you, I think I'm ready to push a little harder now. So we're not going to do these 2. All right? We're not. Because in what I'm going to do with the general formula, I'm not going to use left endpoints and midpoints. So the conclusion is, and we already saw this from the computer program I showed you where we could add a bunch of rectangles. It doesn't matter if we use right endpoints, left endpoints, or midpoints. To get the true area, we need to let n get the number of rectangles get very large. All right? We now try to find that formula, but before we do it, I'm going to talk about some preliminary concepts, some things that we have to know before we can do it. First, sigma notation. So hopefully you've seen this notation before. The capital Greek S, capital S, Greek letter. If you write sigma, and then on the bottom you put something like k equals 1, and up here you put n, and then inside here you put an expression like a sub k. And what this means, the capital Greek S, is that you're going to be adding things up. You're going to start by letting k be 1 and replace that k in there with 1. Write that down. Then plus, now let k cycle up to the next integer, which is 2. Replace this with 2, write that down, then put a plus. Then you go up to 3, put it down, plus. And you keep doing that until you get to what? This top number. Okay? This is called the lower limit of the sum. This is called the upper limit of the sum. And then I gave you a couple of examples. If you come in here, sum k equals 1 to 3, and then here's your expression. So this right here is the a sub k. It's just an expression. You first start with k as 1, put 1 in there, that's what you get right there. So it's 1 plus 2 times 1, you square all that. Then you do plus, now let k be 2, replace that k with 2, figure out what that is, then plus, let k be 3, plug it in here, and when you plug all that in, you stop at 3, right? 3 is where you end, and then you add those up, you get 83. This is another one, k to the k. So you start, plug in 1, 1 to the 1, plus 2 to the 2, plus 3 to the 3, plus 4 to the 4, you stop. Questions? Sigma notation? Now there are some very common sums that come up enough that we need to have formulas for them. Here they are. So look at that first formula up here. The sum k equals 1 to n of k. So this is 1 plus 2 plus 3 plus 4 plus 5 all the way out to n, and then add those up, and what do you get? Now, there's a story behind this, and it's been argued whether or not this story is true. I believe it because I think it's a great story. There's a mathematician named Gauss. If you've ever done elimination, like systems of linear equations, right? We did it. Our calculator did it for us, right? You plugged in the matrix and all that. To do that, the computer is using an algorithm called Gaussian elimination, named after Gauss, who's the mathematician who came up with it. Now, Gauss was a brilliant mathematician. He has a lot of things attached to his name. But the story goes that when he was in first grade, the teacher in first grade gave the students a project that day. The teacher didn't want to deal with the kids. And the teacher said, I would like for you to add up all the numbers up to 100 and tell me what they are. The idea being that it would keep the students busy, and he could go do whatever, update his Twitter. No, wait, this was like 100, 200 years ago. So the teacher was just sitting up there daydreaming. And so the story goes that within a few minutes, Gauss turned his slate, because they wrote on slate, not paper back then. He turned his little like chalkboard slate thing over and sat there very polite, very manners and stuff back then. They had all that stuff. So just sat there quietly. Teacher went up to him, turned over the slate, and Gauss had written on it n times n plus 1 over 2. That's all he had. So he didn't have the answer to this. He just had a general formula. So this formula means that if this right here is n, if that's your n, so here in this case n would be 100, that if I just plug 100 into this formula, that'll tell you what that sum is. And so the teacher was kind of irritated, according to the story, because this formula was known, okay? Gauss did not come up with this formula. The formula was already known. But the teacher was like, someone had to have shown that to him. So he asked Gauss, like, who showed you this formula? And Gauss was like, nobody showed me the formula. And he said, well, where did it come from? So I'm going to show you what Gauss's explanation of this was, and you'll quickly see that what separates us from geniuses, all right? So this is because I think most of you will follow this. All right, so here we go. This is what Gauss's explanation is. He said, I'm supposed to find a sum, we'll call it S, which is 1 plus 2 plus 3, all the way out to 100, right? But because Gauss understood that addition is commutative, meaning doesn't matter what order you add things in, right? You can do 2 plus 1 is the same as 1 plus 2. He said that means S is also equal to 100 plus 99 plus 98, and then plus all the way down to the last number would be 1, the one before it would be 2, the one before that would be 3. Got it? And then Gauss said, well, wait a minute, hold on. If I add these straight down, S plus S should give me 2 S's. 2 of the sums that I'm looking for should be equal to each one of these added down. So what's this? 101, what's this? 101, what's this? 101, what are all of them? 101. How many do you have? Well, you have 1 of them, you have 2 of them, you have 3 of them, you have, in this case, 100 of them, right? How do you say repeated addition is multiplication? So if I want to do 101 plus 101 plus 101 100 times, I just do 100 times 101, right? That's twice what I want, so I just take half of that, right? And that would give me the sum. Yes? Okay, but that's not actually how Gauss explained it. He said, you wanted me to do 1 plus 2 plus 3 all the way out to what? Let's say 100, but he said, let me go to n. What's the one right before that? N minus 1. What's the one right before that? N minus 2, right? Now flip the order of this. Put the last one first. It would be what? n, what's the one right next to that? N minus 1, what's the one next to that? N minus 2, all the way down to 1 at the end, right? And then 2, and then 3. Same approach, add straight down. What do you get? 2s. Now, n plus 1. What is this? N minus 1 plus 2. N plus 1. What's the next one? N minus 2 plus 3. N plus 1. How many n plus 1s will I have? 1, 2, 3, 4, 5, 6, 7. N of them. Oh, so I'm going to have n plus 1s? Yeah? Okay, I want half of that, though. That's twice what I wanted. So divide by 2. That's your formula. First grade. Yeah. So now, how many of you followed that explanation? All right. Now, do you understand what I mean by what separates geniuses from, I mean, when a child sees that, you can't teach that. I mean, that's just something that problem solving is just like hardwired in there. So he went on to do many, many great things in mathematics. So to be clear, he does not get credit for that formula. It's not his formula, but he understood that formula at a very, very early point in time. So back to this. If you want to add up 1 plus 2 plus 3 plus 4 until you get to n, that's the answer. N times n plus 1 over 2. Now, there's another formula that comes up a lot. It's the sum of the squares. So if you want to do 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way to n squared, the formula is n times n plus 1 times 2n plus 1 over 6. You could prove that one also. You can't do it the way that we just did it with Gauss's one. It doesn't work as well. Okay? And I know that there are some people, or I know I've had some people say that they're math majors. If you're a math major, you will have to prove these formulas rigorously using what's called the principle of mathematical induction. You prove that this formula is true. It's a very awesome principle in mathematics, PMI. All right, then this last one, the sum of the cubes. 1 cube plus 2 cube plus 3 cube plus 4 cube, all the way out to n cubed is, hey, that looks familiar, n times n plus 1 over 2, right? Squared, though. All right? So you just need to know that these exist. You need to know the formulas are there. We may need them. Next, we're still with some preliminary concepts here. Some properties of sums. If you have a sum and you have a constant inside there, the constant can come out. You can factor out the constant. So you would just take the constant out, figure out what this adds up to, and then multiply by c. So here we have 3 times k squared. You pull the 3 out. What's the sum of k squared from 1 to n? That's the formula from right above, isn't it? And then the 3's out in front of it. This one right here says that if you have a sum and you have 2 different things being added up, a sub k, b sub k, you can break them into 2 separate sums and you can add them together. This also works with subtraction. So if I have sum k plus k squared, sum 1 to n, I can split it up into sum k equals 1 to n of k plus sum k equals 1 to n of k squared, then apply the formulas to each one of those, and I can get the answer. Make sense? You just have to know that that's allowed, okay? You can't just assume it is. I don't know why I have common sums again. All right, let's do this. I want to find a formula for the estimated area under this graph, f of x equals x squared on 1, 5, using n rectangles. All right? N rectangles. So we're still here. Are y'all with me or not? I want to make sure that y'all are alive. There's x squared from 1 to 5. So what we did before was we found what first? Delta x, right? So delta x, we said we kind of had a formula for it. It's going to be that b minus the a over the number of rectangles I have. In this case, how many rectangles do I have? N. So I'm just going to have to put n. I'm not going to put 5, I'm not going to put 10, I'm not going to put 100. It's n rectangles. I'll tell you what n is later, right? Okay, what else did we find? We had all the points on the x-axis that created the ends of our rectangles, right? So I have like all these rectangles in here, dot, 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 dot. There's a bunch of them in there, right? N of them. The first one here, x naught, then I had what? x1, x2. How many will I have here? Let's go back. How many rectangles do I have here? 4, right? I had x naught, 1, 2, 3, 4, right? 5 points, but it stopped at x sub 4, which means we should stop at x sub n, right? So we are going to have all these points until we get to the last one here, which is x sub n. Y'all still following me? All right. Let's come up with the formula for x sub 0, x sub 1, x sub 2. So x sub 0 is, in our case, a, right? Which is what? 1. X sub 1 is a plus delta x, which should be 1 plus what? B minus a over n, right? That's what it is. What? Oh, we didn't plug in b minus a. What's b minus a? Oops. 5 minus 1 over n. So that's 4 over n. Sorry, go back up here. We never plugged in the 5 minus 1 and got 4 over n. So this, let me replace this with what? 4 over n. We still good? What's x sub 2? A plus 2 delta x's, right? Which will be 1 plus, now watch the way I write this, 2 times 4 over n. I'm not actually going to put 8 over n. I'm just leave the 2 out there. Questions? Next one. A plus 3 delta x, which is 1 plus 3 times 4 over n. And I keep doing this, right? Just keep generating these until I get to the very last one, x sub n, which will be a plus what? N delta x, which will be equal to 1 plus n times 4 over n. Yes, that will cancel to be 4, which makes sense, doesn't it? Shouldn't our last point be 5? Isn't this 1 plus n over n cancels and you just get 4, and 1 plus 4 is 5? Okay, but we're going to leave it like that. You'll see why we're leaving it like that in a second. All right, are we there or not? Yes? Okay, let's try and figure out what the area of all these rectangles are together. So the area is rectangle 1 plus rectangle 2 plus rectangle 3 plus all the way till I get to the nth rectangle. Agreed? What is the formula for the first rectangle's area? So how tall is the first rectangle? It's the function plugging in what? x1, right? So it's f of x1 times delta x plus the next one, f of x2 times delta x plus f of x3 times delta x all the way until I get to f of x sub n delta x. Tell me what f of x sub 1 is. So this is f of, what do we say, a plus, so for us it was 1 plus 4 over n, wasn't it? 1 plus 4 over n. 1 plus 4 over n, and what was delta x? 4 over n. What's the next one here? F of 1 plus, I don't hear enough answers. 1 plus 2 times 4 over n times 4 over n. Next one, f of 1 plus 3 times 4 over n times 4 over n plus dot, 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 what's the last one? F of 1 plus n 4 over n times 4 over n. All right. Let me highlight the only thing that's different in every single thing I put up there, the only thing that's different. And there's a 1 in front of this one, right? There's a 1 right there. So watch what's going to happen right now. You ready for this? This is the same as the sum k equals 1 to n of f of 1 plus k times 4 over n times 4 over n. Do you agree with that or not? So what happens first is that I plug in 1, right? Plug 1 in here, and I get this expression, which is that. Yes? Then I'd say plus. Now I plug in 2. Plug in 2 into this, I get that one. Plug in 3, I get the next one. Plug in 4, I get the next one. And I stop when? At n. Do you agree that that is a condensed version of what I want? Yes. Now I know a lot of you kind of know where we're headed with this, but this is the first time I'll start to allude to why we do this, what this is all. A lot of you know that this is related to the integral, right? The antiderivative. Okay, but the whole reason I do Riemann sums is because the most important thing to me is this. When we write down this, and I always get students that ask me, like, what does the dx mean? Like, what is this thing, right? What this is a version of that. This elongated s represents a type of sum. This f of x represents a height of a rectangle. And this dx is an infinitesimal width. It's a delta x. Do you see that? Somehow that is going to turn into this. That's the whole point. If I just walk in here today and tell you, hey, if you want to find the area under a curve, you just do an integral, and that it works, there's no geometric connection, and it makes other stuff we do later much harder, because the geometry part of it needs to be there. All right? Now, what does it mean to plug this into this function? So what happens when I plug 4 into this function? 4 squared is 16, right? What if I plug in t? It's t squared, right? What if I plug in t plus 1? It's t plus 1 squared. What if I plug in 1 plus k times 4 over n? It's 1 plus k times 4 over n squared. But the f will go away, won't it? So watch, I'm going to do sum k equals 1 to n of 1 plus k times 4 over n, that quantity squared, and then 4 over n. So f has gone away. Let's square this. Okay, let's square it. Let's actually do this over here. 1 plus, I'll write it this way, 4k over n squared. That's the same thing, right? Let's square that. So you multiply times itself. So what would you get here? I'm going to rewrite it in this sum. It'll be 1 plus, that's 1 times 1, then you have 4k over n, then you have another 4k over n. If you take 4k over n, you add another 4k over n. So it's 8k over n in the middle. 8k over n. And then we do the last ones, this times this, and we get 16k squared over n squared. 16k squared over n squared. Now, sitting outside next to all this is what? 4 over n. Can I now push the 4 over n into this parenthesis? Yes. So I'll do that on the next line. Sum k equals 1 to n of 4 over n plus what? 32k over n squared plus 64k squared over n cubed. All right. We are very close. What I'm going to do now is how do I want to do this? I'm going to break it into 3 sums. Am I allowed to break it into 3 sums? Yeah, the properties of sums says I can do that. Now, what I can also do is I can also pull constants out of sums. A constant would be anything that's fixed, right? So on the first one, is 4 fixed? Well, obviously 4 is fixed. Is n fixed? N is the number of rectangles, isn't it? So the only thing in here that would be affected is if it had k, right? Like if k's there, then it's going to change. But if k's not in here, k does not change this at all, does it? Okay, so I'm going to factor out a 4 over n from this one, which would leave a 1 inside there. So it's going to be 4 over n came out of the first one times sum k equals 1 to n of 1 plus, what can come out of this one? 32 over n squared. 32 over n squared, sum k equals 1 to n of k, plus what comes out of the next one? 64 over n, sum k equals 1 to n of k squared. Where? Oh, yeah, cubed. Wow, I missed it up here. Why didn't y'all tell me? Cubed. Right there. I forgot to write it. It was cubed here, cubed here, cubed here. Now, let's talk about what each of these formulas, what each of these sums give us. I have 4 over n times, what is the sum k equals 1 to n of 1? So what I'm supposed to do is I'm going to start with k being 1, right? And I'm going to write down, so I'll do it on the side, I'll do it on a new page. Sum k equals 1 to n of 1. So first start out, let k be 1, and what do I write down? 1. Now plus, now let k be 2. 1. Let k be 3. 1. Let k be 4. When do I stop? When I've done it n times. How many 1s are there? N of them, right? What's 1 plus 1 plus 1 n times? N, isn't it? That's n. So this sum is going to be n. This whole sum gets replaced with n. Okay, that's what that whole thing becomes. Then I have plus 32 over n squared. Now tell me about this sum. That's Gauss's sum, right? That's 1 plus 2 plus 3 plus 4 plus 5. And Gauss said that that turns into n times n plus 1 over 2. And then the next one is 64 over n cubed times, now what does this formula turn into? That's not Gauss's, but n times n plus 1 times 2n plus 1 all over 6. Okay, almost done. Almost can clean this up. I mean, almost done after I clean this up. I have some n's that cancel here, so I get 4. Plus, I'm going to distribute this n through, get n squared plus n, and then multiply it by 32. So on top I'll have what? 32 n squared is 32n all over 2n squared. Oh, I could have reduced it. Could have made it 16, right? Yeah, that's all right. I'll do the next step. Plus, okay, you have to multiply all this out. So let's do that. N squared plus n is what you get when you first distribute here to here. Now let's multiply that times 2n plus 1. So that would give you 2n cubed plus n squared plus 2n squared plus n. So that's what would happen if you got this together. But then we're going to multiply it by what? Can we reduce these? I can what? Do a factor of 2 goes into each of these 3 times, and 2 goes into here 32 times. So let's let's multiply 32 through. So what would I have? 64 n cubed. Oh, I never put these n squareds together. That's 3n squared times 32, 96 n squared, and then finally plus 32n all over 3n cubed. And now this is really bothering me right here. 16, 16, and gone. We okay? That's it. We're done. You asked me, or I asked you to find a formula that would tell you the area underneath that curve between the numbers 1 and 5 if we had n rectangles. Now tell me how many rectangles you want. You want me to do 2 rectangles? I just plug 2 into this. You want me to plug in 10 rectangles? I just plug 10 into this. Understand? But what did we say we would want to get the true area? We would want to let the number of rectangles become infinite. And so now what we're going to do is define the true area. We're going to look at this expression, and we're going to let n go to infinity. Right? So this is the answer to that problem. This is our formula. But to get the true area, I'm going to grab this thing to take it to the next page. The true area will be equal to the limit as n goes to infinity of what? This whole thing. That didn't work. I have a different idea. Let n go to infinity here. Yes. Well, remember that geometrically what we said is that every time, if we say like 5 rectangles, it's going to be off, right? We're going to have error. The better estimate is to let n get bigger and bigger. Theoretically, if we let the number of rectangles become infinite, we actually do get the true area, don't we? That's what we're doing here. We've come up with a formula at the end that now we have control over n. We can let n be anything we want. So why don't we let it become infinite? And what we get is 4 plus, infinity over infinity, right? Cal 1. If you let this n become infinite, you get infinity on top and you get infinity on the bottom. How do you handle infinity over infinity like this? What can you do? L'Hopital's rule. L'Hopital. So I'm going to do L'Hopital, even though, you may know that with polynomials, if they have the same degree, it's just going to be this leading coefficient over this leading coefficient, but I'm going to do L'Hopital. So on the side here, I do, limit n goes to infinity of 16n squared plus 16n over n squared. Take the derivative of the top and bottom. Have y'all seen this? Like L'Hopital, you put a little L or an H on top of the equal sign to let everyone know you're doing L'Hopital's rule. How many of you have not seen L'Hopital's rule? Anybody not seen? Did you take Cal 1 here? No? Okay. You're going to need to look it up. Or maybe you have and you don't remember. It's the name. That's an important concept. It's going to come up a lot in this class now. So L'Hopital, take derivative of the top divided by derivative of the bottom. What's the derivative of the top? The limit's still here. 32n plus 16 over 2n. That's still infinity over infinity. Apply L'Hopital's rule again. I put an L. I don't like the H. I don't know why. I've just never liked the H. So I do. So you get on top 32, and on the bottom you get 2, and that gives you 16. So this turns out to be 16. And if we do the same thing on this one, because this is infinity over infinity, if we were to do L'Hopital on this, we would get what? 64 over 3. So this is 20 plus 64 thirds. Let's get a common denominator. What's that? 60 thirds plus 64 thirds, which is 124 thirds, which is approximately what? 41.333 repeating, which is the true area. So what I'll do is I'll go back to this thing I had here. I'll put x squared in here. Here's x squared between 1 and 5. The true area is 41.333. We let the number of rectangles go to infinity, and we got closer and closer. In fact, by letting it go to infinity, we got the true area, right? Exactly. However, all of this work, again, leads us to where? I mean, we obviously do not want to have to do this each time. And that's why it was so critical that the fundamental theorem of calculus was discovered, right? The fundamental theorem of calculus gives us a way of doing this using the antiderivative. And that's what we'll spend next class on. We're not going. Don't start packing up. So here's what we determine later, and we'll write it down formally. I'll have notes to give you. If you have a function and you're looking from A to B, and you'd like to know the area under this curve between here and here, if you want to know that, that area will be equal to the antiderivative of that function. That's what we just spent 6 weeks on, right? But we're going to add these two things on this integral symbol. We're going to put the a down here and the b up here. These are what are going to be called the limits of integration. That tells us where our interval is, all right? This turns out to be equal to, remember the antiderivative is capital F, right? It's the antiderivative and then this is just notation. Just write that down. I'll tell you what that means. This next equals tells you what this means. It's capital F of B minus capital F of A. This is basically a version. There's two versions of the fundamental theorem of calculus. This is like the second version. So if you want to know the area under a curve, right, what this actually turns out to be is the antiderivative evaluated at the endpoint B minus the antiderivative, that's capital F, evaluated at the endpoint A. It's beautiful. Look at this problem we just did, right? Trying to find the area underneath x squared, right? Between 1 and 5 means I would write 1 to 5. The function I'm trying to integrate is x squared, or trying to find the area under, right? According to this, that will be equal to, first write down your antiderivative. What is the antiderivative of x squared? 1/3 x cubed. Then we write this line and we put 1 and 5 here. So this right here just gives us an opportunity to write what the antiderivative is. There will not be a plus c here. Right? There will be no plus c. I'll explain why next class. This should equal, now, capital F of B, that means take this, plug in, what, 5? So this is, I like to do two big sets of parentheses. This first one is going to be F of B, capital F of B. This one's going to be capital F of A. So 1/3, 5 cubed. This next one is going to be 1/3, 1 cubed. What's 5 cubed? 125 over 3 minus 1/3, which is 124 thirds, which is exactly what we just spent 45 minutes on. Right? Now, let's go back. Just try, see, because I mean, I kind of want to know from you, and it may be too early to poll you. I could have started class with this, and we just go on, okay? My whole purpose of showing you the Riemann sums is, again, for you to understand this integral sign is what happens when you take that sum and you let the limit, the n, go to infinity. That's what that is. This is the height of the rectangle. This is the width of the rectangle, right? I think that that's valuable. Hopefully you do. Don't give me your opinion yet. I don't want it. Never mind. Let's see after we do when we start revolving things around different axes and you're having to come up with the formulas for these geometrically, I think that'll help, the concept. All right, I wanted to do area of circle. I wanted to do it before we ended class. Let's try it. Okay, so we have a circle, right? Let's say this is the unit circle. The unit circle has the equation x squared plus y squared equals what? 1. That's the equation of a circle, yes? Centered at the origin, radius 1. I want to know the area of it. To attack this problem, what I'm going to do is this. Oh, you know what? We don't want the radius to be 1. Scratch that. Let's try to be harder than that. Let's make the radius r. So why don't we do r squared? That's the equation of a circle, isn't it? Radius r. So I want to find the area of the whole circle. I'm going to focus on just this first quadrant. What I need to do is come up with a function that draws that top right corner of the circle. So what is the function? What is the function that would draw this curve? I have to take this equation right here and solve it for y, right? Then it would be y as a function of x. Sure? So if I solve this for y, I would get square root of r squared minus x squared. So you would have taken the x squared to the other side by subtracting it. Then you would have done square root. And you would have had plus or minus, but that's okay. The plus is the top part, right? The minus is this bottom edge. We're not looking at the bottom edge. So do you agree that if I graph this right here, it should draw this top right piece? Yes? Okay, so now let's talk about where our restrictions. We're looking in this blue region. What's this point right here? 0. What's the end point right here? Little r. Do y'all see that? Little r. So according to what I just told you, the fundamental theorem of calculus thing, all this really turns out to be is this integral sign. I put these two limits, right? 0 and r here. Then the function that I'm trying to find the area of, which is this, dx, right? Remember, r is a constant. How would you do that problem? Well, you could go to your formulas, right? But we still have 7 minutes, so I can do it without a formula sheet. I'm going to use trig sub. I'm going to use the trig sub. Remember, this looks like a squared minus x squared. So I'm going to use the trig sub. X is equal to a sine theta, but a is really what? R. So r sine theta. Dx in this case is r cosine theta d theta. And then the square root of r squared minus x squared should turn into r cosine theta. Rewrite the integral. This integral becomes, now notice I took my things off here. 0 and r, notice I took them off right now. The reason I took them off is because we're changing variables. And that makes a big difference. Now, hang tight. So, rewrite this, what do you get? R cosine theta, what's dx? R cosine theta d theta. Let's work on this. R is a constant, it comes out, r squared. Then I have, what's still in here? Cosine squared. How do you handle cosine squared? Half angle identity, it's the 1/2, blah, 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 cosine 2 theta. So the 1/2 I'm going to bring out, and then I'd be left with in here 1 plus cosine 2 theta d theta. I can take the antiderivative of both of those. Antiderivative of 1 is, so no more integral sign here. This is theta, then this is plus half sine 2 theta. I hear people following me, so I'm happy to keep going. And then I'm supposed to have plus c, right? But we'll get to that. At the end, we're not going to need the plus c. Think about it. Look, capital F of B minus capital F of A. If this one right here turns out to have a plus c in it, and then over here plus c, these c's cancel each other out. Like it's c minus c, so they're gone. So we won't need it. But I do need to get back to x. Let me get back to x. So how do you determine what theta is? I'm going to, yes. I'm going to do that. What's theta? Go back up. Arc sine of x over r. Arc sine of x over r. And then this one, I would, before I do anything, I would take that, I would rewrite that as 1/2 times 2 sine theta cosine theta. The halves would cancel. What is sine theta? We already saw that right here, right? Sine theta is x over r. So this would be plus x over r times, what's cosine theta? I could draw a reference triangle, couldn't I? But it's also right here, isn't it? It's square root of r squared minus x over r. So square root of r squared minus x squared over r. All of that is my antiderivative, isn't it? Now, what I'm supposed to do is find the antiderivative, which I've just done, and because I'm really running low on time, this is going to look real sketchy. Now I want to evaluate that at two places. So I'm using that notation to put in my two integration limits. What were they? 0 was the bottom one, and r was the top one. Yes? Sorry, it's not very neat. I really just wanted to get to the answer so you could at least feel like we did something valuable today. So now let's plug in. This is going to equal something, the r plugged in, then the 0 plugged in. So plug in r. Everywhere you see an x, plug in r. R over r is 1. What's arc sine of 1? So that means on the unit circle, where is sine 1? Where's the y-coordinate 1? Pi over 2. At pi over 2. So we're going to get 1/2 r squared times pi over 2 plus, now plug r into this one. R over r is 1. What happens here? R squared minus r squared gives you 0. That zeroes that whole thing out. Zeroes that, so you just get plus 0 here. Now plug 0 into this. 0 over r is 0. What's arc sine of 0? So where on the unit circle is your y-coordinate 0? At 0, so that's 0. And then plug 0 in right here. It's 0, so that's plus 0. So your answer is, we got 1/2 r squared times pi over 2, which is 1/4 pi r squared. Yes? But that was only the first quadrant. So multiply times 4. You get pi r squared. Right? There you go. So that, now that's just one of many formulas, and this is, one way you can get to them. Here's what I want you to do for homework. Let's see if you can do one. I'm going to send you with one problem, okay? I want you to estimate, or no, let's see, find the true area under f of x equals x cubed on, I'm going to be nice, 0, 1, using Riemann sums. Then verify with this computation. Do you understand what I mean? Okay. It's a long problem. Let's turn it in next class as a quiz grade, all right? If you need help on it, help each other out or come get help. Pardon me? Yeah, but I'm only going to have you on 0, 1. It's going to make it a lot easier. The endpoints 1, 5 that we had previously kind of complicated things a little bit. That's going to come out real clean.